right, so today we're going to look at section 8.6. This is Dual's theorems and nth roots. So this is basically complex numbers revisited. So let's take a look at some of the notation and some of the things that we're going to be asked to do. So a complex number is in the form a plus bi. There's in a number plane. This is the real axis. This is the imaginary axis. So this would be some point in the complex plane. This is the complex number a plus bi. So that is the z is the complex number. So based off of this, we can kind of look at it in the same sense as we did vectors and such. So the length of this, the distance from z to the origin, would be the length of this segment right here, and that is the absolute value as such. Remember, absolute value means the distance this number is from the origin. And to solve what this is, it's simply the Pythagorean theorem. A squared plus b squared is c squared. Okay? If I look at it from a trig point of view, this is the angle in which this line is set up on the real axis. I can find this direction angle right here by using our tangent of theta is b over a. And I also have that this a, based off of the definition of cosine of an angle, is r times the cosine, r being this length, and b is r times the sine of theta, again, r being this length. Okay? So we're going to use that concept to help us in solving some things that make dealing with complex numbers a little bit easier. So here's a polar form or trig form of a complex number, which I kind of started to point out to you up there. Okay, if A is this quantity, r cosine of theta, and B is r sine of theta, then this complex number replacing A and B with those values and factoring out the common factor of r gives you this format, the polar form or trig form of a complex number, where r is the distance the complex number is from the origin, and again the tangent of the angle is b over a. So this is how we can transform one form to another. And this is what you're going to be asked to do first. Can I take this right here, this complex number, and put it into polar form? So I'm going to show you how to do that right now. So z is 2 minus 3i. The first thing I do is I would graph this here so I know what quadrant it lands in. So a is the real, b is the imaginary. So we have a point down here. This is 2 minus 3i. That is my z. And that then would be that distance to the origin. So if I want to put it in polar coordinates, I need to find this angle. In this case, this angle right here. Okay? This will be my theta. A is 2, B is negative 3. And I want to find this distance right here, which will be our r. So let's start with that. So I know that r squared is the square root of 2 squared minus a negative 3 squared. Excuse me, plus a negative 3 squared. And so that gives me the square root of 13. No, I shouldn't do it that way. R. I did the square root. So r is the square root of 13. So the tangent of theta is a negative 3 over 2. So that means theta, because this is negative in the nature of the inverse tangent, this is going to be a reference angle to the one we want. Because the inverse tangent gives me angles between negative pi over 2 and pi over 2. So this angle is the wrong angle. It'll be the negative angle. I want the positive of that angle. Okay. So That means I'm going to have to take this angle for theta, take this angle right here. It gave me this one. I want the positive one, so I need to add 2 pi to that. And in doing so, I get the approximate value of 5.300 in radians. So now I have everything I need. I can put z into polar form, which is the square root of 13r, the cosine of this angle in radians, 5.3, plus I times the sine of 5.3. And there you go. So what would be the reason to do something like this? Well, this guy named Moivre, he came up with some rules, okay, that allows us to multiply and divide and raise complex numbers to powers in a much quicker fashion. Now, for 1 or 2, it's not that big a deal, but if I have it in constant polar form, then I can do these rules. I have 2 complex numbers in polar form. If I multiply them together, it is the equivalent of multiplying the 2 r's together times and then adding the angles, that angle plus that angle. If I divide them, it's like dividing the r's and then subtracting the angles. Again, making sure that the top one is the first one here. So you might get negative angles in here, which is fine. And if I have, I'm going to raise it to a power, and I just take the r and raise that to the same power, and then that exponent up there gets multiplied to the angle inside. So let's see how this might work. Now again, it doesn't mean all problems are going to be easy this way. What I'm going to do is I'm going to walk you through getting them into polar form again, and then using these rules to do those problems, okay? So here's the example we're going to be doing. So Z1 is going to be 1 minus I. C2 is going to be the square root of 3 plus I. So the first thing I want to do is put these into polar form. Okay, so A and B. So we need to find the R first. It'll be 1 squared plus a negative 1 squared. No I is involved in this. And so this gives me the square root of 2. The tangent, by the way, I should put it into our 1 negative, so it's down here again. So the tangent of theta is a negative 1 over 1, which is negative 1. So the quadrant 4 angle, where it's negative 1, tells me that my angle is going to be 7 pi over 4. And so in polar form, Z1 would be the square root of 2, the cosine of 7 pi over 4, plus I times the sine of 7 pi over 4. Square root of 3, 1. So this one is in quadrant 1, which makes it a little bit easier. So my R is going to be the square root of the square root of 3 squared, 1 squared. And so that's going to be a 4, so it's 2. The tangent of theta is 1 over radical 3. And from that, in quadrant 1, we know then that the angle is going to be pi over 6, because that's what the tangent is, 1 over square root of 3. And so Z2 is going to be a 2, the cosine of pi over 6, plus I times the sine of pi over 6. So with these 2 forms now, I can actually figure out very quickly Z1 times Z2. Yes, I could have just multiplied those out and gotten the same answer, but I'm showing you how these rules work. So the first step here is to take the two r's and multiply them together. And then we take the two angles and we add them together. Add the fractions. And then we put it back into regular form. You'll use a calculator, figure this out, times it by that. Round it to 3 decimal places. And there you go. What if I want to divide them? Take the square root of the top one, the bottom one, and now we're going to subtract. So the first one minus the second one. If they want you to keep it into polar form, then you would be done at this stage. But if you need to put it back into regular form, just use your calculator and work these out and round to 3 decimal places. In this one, we're going to take Z1, we're going to raise it to the third power. So according to the rule, I take the R, which is the square root of 2, and raise it to the third power. And then I take the cosine, and I take that angle, and times it by 3. So it'll be 3 times 7 pi over 4, the sine of 3 times 7 pi over 4. So working that out, this right here would be a 2 times the square root of 2, the cosine of 21 pi over 4. And again, we can work these out. Now, we already know 21 pi over 4 is one of our special angles, so we can actually figure that out and get an actual accurate answer, not an approximate. And in doing so, this right here becomes 2, the square root of 2, the cosine of this, and you can figure out that the reference angle where this is, and it's going to be a negative square root of 2 over 2, and this one over here is going to be negative square root of 2 over 2. It gives me my final answer of this. So if you can find an exact answer, you should do so. Okay? You'll be allowed to write these notes on a note card, these rules to use on a test. I'm looking to see whether or not you can use the rules, not that you have memorized them. The next thing we're going to be looking at is finding the nth roots of a complex number. Okay, so in this case right here, this is the formula. If you're looking for, let's say, a cube root, know that there is 3 distinct complex numbers that can make that cube work. And so you're going to be asked to find them all. And that's what this formula does for you. Okay? K is the counter. It's going to go through all the numbers up to 1 less than the index. So whatever that number is right there, you're going to go 1 less than that in here because 0 is going to be the first number. Okay, this takes a little bit of time to do, but it's not difficult. All right. Again, you want to make sure you add this to your note card so that you can use it on a test. So let's do this example right here. We're going to find the cube root of that z right there. All right. So when k is 0, your first root is going to be the cube root of 2, and then it's going to be the cosine of the angle plus 2 pi times k all over the index, which is 3. And then for the sine, you just write the same thing again. There's the first part. What happens when k is 1? Again, the cube root of 2, you have the cosine. Same thing again. This time k is 1. See, so it just takes a little bit of time to write it all out, and then we'll have to simplify it. But it's not that difficult. And then the last one is when k is 2. See, 1 less than the index. So once you have the formula done, now you have to go back, take all 3 of these, and simplify them out. So now z1 is the cube root of this. We need to work this out. Well, that's a 0. So it's just pi over 4 divided by 3, which would be pi over 12. So this is the cosine of pi over 12. And the sine angle will be exactly the same. Then you do z2, and you work that one out. You get the cosine of what angle? Okay, so you work that out, and you'll figure out that this angle is going to be pi over 4 plus 2 pi, and then you take that and divide it by 3. And what you end up with on this one is you're going to get 3 pi over 4. And then we do the last one, cleaning that one up. And if you work all this out in here, you're going to get 17 pi over 12. If you look at this one, is 1 over 12. This right here would be 9 over 12. And then 17 over 12. You'll notice that they are 8 over 12 apart. Now, the next thing you want to do here is this is the polar form. You want to give, a lot of times they want you to give the approximate value on a calculator. So you would just work this out on the calculator, make sure you're in radian mode, round to 3 decimal places. And then this one right here would be negative 0.891 and 0.891i. And then this is the approximate. And then this one down here would be negative 0.326 and 1.217i. And you will notice, see how these numbers are just flip-flopped. You'll see that kind of action going on. So if you don't see any kind of repeated numbers, that means you have a number wrong. And so that's how you use the nth root. So again, you'll have problems on the test that will ask you to do these. So just make sure you have these rules in your notes and you know how to use them. And so that is 8.6.